Okay, better late than never. Cool. So yeah, lowered phase voltage to a three-phase motor will not harm it if it's connected in the application which is designed. Lowered voltage will result in other forms being loaded, such as the current draw, output power, and torque production. If the voltage across each winding is reduced from 400 volts to 230 volts, then there is also a proportional drop in current draw. There are two ways we can look at this. So the relationship is 400 over 230 equals 1.74 or equals the square root of 3. The percentage lost, 230 over 400, 0.575, so 57.5% loss. With regards to electric motors, torque is proportional to voltage squared. This means that with a reduction in voltage, there is a substantial reduction in torque. This can be expressed as the following. 230 over 400 squared equals 0.33, so 33% loss in torque. Yeah, I can email through, I can get a class list and email through the slides. That's no problem. Can everyone post their email into the chat, because I am realizing that some of you guys might not be on my SAMs for marking attendance, because some of you guys have been given the link to the sessions via, hold on one second. Yeah, just drop them in, unless obviously you've emailed me before, like Ollie. All good. I will endeavor to go through them. And also, while we're at it, in case you guys need it, here's my email address. Cool. So, moving on. Star Delta Starter. Cool. So, Star Delta Starter is most commonly used method for starting of a three-phase induction motor. And Star Delta starting an induction motor. So this was before we had VFDs. So it was more common before we had VSDs and VFDs. Once the motor reaches the required speed, the motor is connected through to Delta. So it starts in Star for reduced starting torque and reduced power. And then it goes into Delta for full load torque and full load power. So motor reaches about 80% of full load speed, it'll begin to run in Delta connected stator winding. The Star Delta starter is a type of reduced voltage starter. It was used to reduce the starting current of the motor without using any external devices or apparatus. It's a big advantage of a Star Delta starter, as it typically has around a third of the inrush current compared to a standard DOL starter. The advantages: it's inexpensive, no heat is produced or tap changing devices needed to be used. Starting current reduced to a third of direct online starting current. It produces high torque per ampere of line current. Disadvantage: starting torque is reduced to 1/3 of full load torque. A particular set of motors required. Cool. So here is the power and control circuit drawing. So if you look at the top, you have the control circuit up the top, and down the bottom you have the power circuit. Cool. So if we look at the top, so we have our circuit breaker, our e-stop, and our stop button. We have a start button and the main motor contact. So that is the main motor contact here. And then in line with that, we have our motor overload and our M coil. So that's what starts it. As soon as we hit the start button, it latches the M coil above the start, and it also starts T1 timer. So the T1 timer will engage the delta contact. We'll go through the delta normally closed into the star contact. Once the star contact coil is engaged, the star normally closed in front of the delta coil will open. So we can't have delta and star going at the same time. So we have this electrical interlocking. to stop us from being able to turn on both at the same time. And then as soon as it's reached 10 seconds or however long, then T1 normally closed will open, which will stop the star coil, and the star normally closed will shut again. The T1 normally open will close, which will send current through the star normally closed into the delta coil, and it will click in and delta will begin to spin. So this is one of the things you will have to wire up as part of your year 2 or year 3 block course. So have a look at it now and obviously be a good resource. Cool. Now I believe there is. Cool. So they did it. They showed it with one less contactor than you would normally use. You would normally have 3. One for your main power, one for your star, and one for your delta. Cool. So as well as the configuration in which we connect a 3-phase motor, there are other considerations we must take into account. So these may include the environment the motor and associated fittings are going to be installed in. This includes cable routes, mounting location and techniques, blending of cables, terminations, and the connections. The installation methods and techniques required, including site analysis and hazard identification. Correct installation of the motor. Are the guards fitted and secured properly? Are ventilation ports free from obstruction? Are there any protective coatings that need to be removed prior to operation? Once installed, does the motor test out with adequate test results? Do the earthing, insulation, resistance, and phase rotation results comply with the requirements? Once the motor is running, current draw, direction of rotation, temperature, and vibration effects on the motor. Cool. So installation of a 3-phase motor. Before installing a 3-phase motor, there are a number of factors to consider. Firstly, the load for which the motor is intended to operate under. Such considerations regarding the load type include the inertia of the load, the speed and direction control, starting speed, etc. An appropriately sized motor must be selected in the first instance. Mounting arrangements for the motor. Can it be flange mounted or does it need to be foot mounted? How will the load couple to the shaft to the motor? How sometimes an appropriate structure must be designed and fabricated to fit the motor to suit. This may also include the environment the motor is to be used in. Is it wet? Is it explosive? Is there fine powder in the air? Will there be steel shavings? Is it a machine shop? Is it a flour mill? Is it going to be a wet area? Does it need to be a totally enclosed submersible motor? Supply arrangements for the motor. What size cable will it require? What type of cable will it require? If it is driven by an electronic speed controller, it should be a shielded cable to minimize electromagnetic interference. What sort of protection and control equipment does the motor need to work alongside it? Initial and ongoing costs should be considered. How often will the motor and associated equipment require maintenance? So all of these things need to be taken into account. One job I did last weekend was I went and replaced a roller door motor in Maupuia, which sits above Miramar. Obviously, it's quite close to the sea, so it has a lot of salt air. It was a standard light commercial roller door motor that was not completely sealed, so it was quite affected by the sea salt in the air and moisture. So it had been affected by moisture. It had moisture ingress, and so the windings and relays inside the motor had gotten too wet and it stopped working. It was also plugged into a standard domestic double vertical power point, mounted in a exterior parking garage, open to the elements. The installers were geniuses. Cool. So current values and power values. So, cool. So the amount of current a 3-phase induction motor will draw depends on a number of conditions. So the voltage being applied, output power, efficiency, and power factor, where P equals the output power measured in watts. VL, voltage line measured in volts. IL, line current measured in amps. Cosine theta, the power factor value. And the efficiency expressed as a percentage. So with this equation in line, P equals the square root of 3 times VL times IL times cosine theta times N being the efficiency. A three-phase motor is connected to a supply with a line voltage of 400 volts and is drawing 5 amps. Assuming no losses, what is the output power of the motor? Cool, so I'll give you the formula. P equals square root 3 times VL times IL. Yep, so P equals square root of 3 times 400 volts times 5 amps, which gives us 3464.1 watts or 3.46 kilowatts. Cool. Three-phase motor is connected to a supply with a line voltage of 400 volts and is drawing 8 amps. There's a power factor of 0.8 and efficiency of 0.09. Calculate the output power of the motor. So our formula is P equals square root of 3 times VL times IL times cosine theta times efficiency. I think it's eta. Cool. So we put the values into the formula. We get square root of 3 times 400 volts times 8 amps times 0.8 times 0.9 gives us 3,990.65 watts or 3.99 kilowatts. Cool. Cool. So I won't give you the formula. Three-phase motor is connected to a supply with a line voltage of 380 volts and is drawing 9.5 amps, has a power factor of 0.75 and an efficiency of 0.7. Calculate the output power of the motor. Okay, cool. So we take the formula, P equals square root of 3 times VL times IL times cos theta times efficiency. Square root of 3 times 380 times 9.5 times 0.75 times 0.7 gives us 3,282.7 watts or 328 kilowatts, 3.28 kilowatts. Cool. Starting current. So while there is no simple way to accurately calculate the startup current of a motor, it is typically viewed as being about 6 times greater than full load current or 600% greater. We must install our wiring systems and circuit protective devices accordingly for these situations. For instance, a GM rated HRC fuse would be used to protect the motor, or a motor type circuit breaker, as it can handle a larger degree of current for a few seconds before operating to allow the motor to start. Cool. To torque. So we'll start at the beginning. Due to the high current flow in the stator windings and the large relative speed difference between the stator flux and the rotor starting torque of a three-phase induction motor, it's typically looked at as about 200% full load torque, FLT. So this graph indicates that as a motor speeds up, torque builds up as well, up to roughly 80% full speed when the motor reaches breakdown torque. This is when the torque begins to decrease as speed continues to increase until the running torque matches the load torque, At this point, the speed of the rotor will stabilize, typically at about 95% stator speed or 5% slip speed, if the motor is rated appropriately. Different situations call for different values of starting torque. In some instances, this 200% full load torque is not enough to overcome the inertia of a load at low speed. If the motor cannot overcome the load at startup, it will not start at all, and the motor will remain stalled. This is not good. Either a more powerful motor is required or a different type that offers a greater starting torque. In other instances, 200% full load torque is too much for fragile loads. Sometimes a motor shunting a conveyor belt into life may cause the load to shift and topple over. In this case, a lowered value of torque is required and can be achieved through means of various motor starting methods, such as star delta starter or electronic starting methods like a VFD or VSD. So basically what they're saying is it needs 200% full load torque at the beginning to get over the initial friction or moment to build inertia. But obviously sometimes 200% isn't enough because it's a heavy load, and so we need more starting torque. Cool. Direction reversal. Cool. So changing the direction of a rotation of a three-phase motor is relatively easy. Swapping over the supply phases changes the phase rotation of the supply to the motor, and thus the rotation of the magnetic flux from the stator. So here we have the control and power circuits. Take a closer look at the control circuit. So we have a circuit breaker, a stop button, an e-stop button, and here we have two separate branches. So up the top we have a forward press button or a push button, and we have in parallel with that, we have a forward normally open contact. We have our forward overload, and then we have our reverse normally closed contact. And then we have our forward coil. So if we push the forward button, current flows through the button, through the overload, through the reverse normally closed, into the forward coil. This latches the forward normally open, that's in parallel with the forward push button, and opens the forward normally closed contact that is on the lower branch, which is for your reverse. This means we can let go of the forward push button, and because the current can flow up and over it through the forward normally open contact that has been closed, we can now have the motor operating in forward mode. But because this forward normally closed on the reverse has opened, we cannot push the reverse start button. This is another example of our electronic interlocking or electric interlock. So then we have to push the stop button. We would, of course, wait for the motor to stop spinning, and then we can push the reverse button, which will do the same process but for the reverse, and it will open the reverse normally closed on the forward branch. So that is how the control circuit works. You will have to do this for your second year block course. So when you're sitting there going to do your motor diagrams, feel free to watch this video back on YouTube and quickly jot it down. And then this is your power circuit. So here the motor is connected in star, just for ease of use. And as you can see, the connections on the top side or the left-hand side of the coils are red, white, and blue. But on the opposite side, the reverse, you have coming out of the blue, going to the red that comes out of the forward, and the red coming out of the reverse contact goes to the blue. So we're on the back side of the contactors, we're swapping the red and blue phases to reverse the spin of the motor. Cool, so the advantages of three-phase induction motors. So there are a number of advantages to using a three-phase induction motor for a range of applications. They can be Simple in construction. There are very few parts that can fail compared to that of other motors. We don't have to worry about capacitors blowing or centrifugal switches failing. Cheap to manufacture. Due to their simplicity, these motors can be manufactured quickly and for a very low cost. They're safe to use due to the lack of external brushes and slip rings. These motors do not spark and can be completely sealed, meaning they can be used in hazardous areas. Self-starting, so three-phase motors are able to start themselves without the need for extra starting equipment. They have good torque speed characteristics compared to some other motor types. These motors have relatively high running torque. They also provide much smoother torque than single-phase induction motors. There are some disadvantages. So with all things, the three-phase motors also have their share of disadvantages, such as inrush current. So due to their inductive nature, three-phase motors draw a great deal of current during startup. This must be accounted for during the design phase of installation. So power factor, induction motors always have a lagging power factor, but this value is at its best when the motor is fully loaded. An induction motor that is lightly loaded suffers from a much poorer power factor. Due to speed control compared to the other types of motors, three-phase induction motors can be relatively tough to finely tune in regards to speed. Nowadays, electronic speed controllers make this job easier, but compared to other motors, it's a complex